Okay, the purpose of this video is to kind of get you, we've been doing a lot of different parts. Now we're basically up to full speed. Give me just a sec. All right, so I want to talk about some special tricks that can speed up your life, but the first time you see them, it's like, what? Okay, when we're doing this equation, if we plug in a bunch of numbers, obviously we might have different things like, let's say V was equal to 3.0 meters per second. Let's say T was equal to 4.7 seconds. Forget about sig figs. Let's say A, which is an acceleration, was 3.3 meters per second squared. And I think that's all the terms here. You might be saying, oh, we could figure out delta X. Now, a quick comment. X, we know, has been, for the last several problems, X is a length or something here. This is a change in a length, but that's still going to be subunits, right? You could think of this as X final minus X initial. Well, if this is in units of meters and this is in units of meters, you might be saying, wait, does that give me no units? No. Let's say I had 7 meters minus 2 meters. The answer would be 5 meters. So I just wanted to point out here, obviously I don't know these numbers, but in this case, these might not match up to those. So I'm going to erase this in just a second. The point is a change in distance has the same units as a distance. That's what this was about. These are not the right numbers. I'm erasing them. Okay. So said simpler, I'll say it this way. Note, delta X has same units as X. That's what I just said. And now it's written there. Okay, you could punch in all these numbers and figure this out. One thing that we typically do when we're doing physics equations is I do not want to write all this garbage down. I do not want to be thinking about these units all the time. So one of the things that we'll do is we'll very quickly, before you plug in the numbers, quick run the units. So this is meters, and I'm going to see, is this right? I've got meters per second times seconds, looks like meters, plus 1/2, that's no units. So I'm not going to write it. No units is 1. And then A is meters per second squared times seconds squared. And notice this fact. We see that on this side, the units of one term are equal to either of these two terms. Said in with these unit math brackets, we're assuming that the units of delta X should equal the units of VT. Now, I'm not saying that delta X equals VT here. I'm saying the units of this term only should equal the units of this term only, and they do, right? But I know from experience that meters plus meters, when I'm doing unit math, should give me something else in meters, right? 3 meters plus 8 meters is 11 meters. So the units, when you're doing addition like this, meters plus meters is meters. All right, notice I can also do this. The units of delta X equal the units of 1/2 AT squared. What I'm saying here is not that delta X equals this. I'm saying the units of this term should equal the units of this term, or the dimensions of that term. Okay. Now, at first you might be saying, well, who cares? In practice, a great many equations that we work out in physics will have complicated results that have addition and subtraction and multiplication all over, and you can get multiple terms like this. This is a real physics equation that we'll talk about in chapter something, 1D motion. But in the reality, you might get an equation that looks like, come on, there we go, like this, which is ugly. And what we want to do is we want to be like, I need to check these units, or maybe this is a given equation in a textbook and you're trying to get a feeling for it. So you want to understand these constants. We might want to check the units and see if the units of each term match. Now, the way I phrased it here is I'm going to try and figure out the units for alpha and beta. So let's assume that alpha and beta are two constants. Now, if you try to solve for alpha using algebra, it's going to be ugly. Or try to solve for beta, it's like, woof. But what we can do is, if all I want is the units, I'm going to use this new trick. I'm going to say the units of the square root of alpha X should equal Well, I'm gonna look at this one. I don't know what beta is, so I'm gonna ignore that term, but this one, I kind of know this one. Ooh, let's change G just to A, so I don't have to explain what G means. Apologies. So let's say this one is times the units of M, A, V over T. Now, right away, this is a lot easier to deal with because we're comparing the units of these two terms only. I don't have to worry about this thing that I don't know about. So in this case, I'm like, how am I going to get this? I like to oftentimes plug in the units at the very last step. So for me, I might get rid of the square root by squaring both sides. I'm going to square both sides. That's legal. It's just like algebra. And then when I do that, the squared will cancel this. And now I'm going to write it this way. The units of alpha should equal the units of M, units of A, units of V, all over the units of X and the units of T. And I'll get out of the way and explain this. Again, look what I did. I squared both. Oh, crap. I forgot the squareds. So every term on this side should be squared. And then over here, this square got rid of the square root. And then I just divide by the units of X. At this point, we can crank this out. It's ugly. This equation, by the way, is completely made up. It's just I was trying to make it so that we had to practice. That's all. So I'm going to have kilograms squared, meters squared per seconds to the fourth, because A is meters per second squared. You got to square the both. Oh my gosh, times. Oh man, why did I pick this problem? All over, geez. Oh, this one is a meters. This one is a second squared. And then what do I like to do? Not screw it up. And a lot of you might be thinking, he would never put this. I would. Okay, I would put this on a test. I would just make it difficult to see if you could follow the rules, because this is not that hard. Okay, it's just time. But we do see this meters will cancel one of these. So out of all this, I'm going to try and get in here and write this. Oof. I got on the numerator kilograms squared, and I've got meters squared times meters cubed. Then in the basement, I've got seconds to the fourth, second squared. So what is that? Seconds to the eighth? Oh my gosh. That's crazy. So, okay, it's weird, but that's fine. This is just good practice. All right. So now that's part A. The units for alpha are this thing. All right. If you want, try to get the units for beta really quick. Pause the video. I'm going to do it right now. So you can unpause when you're ready. So the units of beta, I'm going to say, you could use either one of these. I don't know which is better. So I'm going to, you know what? I might just go with this one here again. I'm going to compare these two. You could compare any two you want. Now we know the units of alpha. I just don't want to deal with that square root again. So I'm going to go here and here. I'm going to say the units of M, A, V over the units of T equal, the minus sign doesn't matter. So it's the units of beta squared and the units of V cubed all over the units of A. Ugh, this is ugly. So just like last time, at this point, what I did was compare any two terms that we know. Now I'm going to try to work towards isolating this term, which is what I care about. That's the big deal. Instead of solving algebraically for beta in the original equation, first slap on the units, compare two terms, then move things around for beta. So in this case, I think, oh, this is going to be kind of weird. Oh, this is really weird. So I'm going to switch the sides and write beta squared equals all of this junk, M times the units of A times the units of V all over the units of t. And then what I'm gonna do is bring an a up here and a b cubed down, so. This problem's getting complicated, so rather than try and do cancellations in my head, I'm gonna write it down. So let me see. I did a lot here. I switched the sides, but I also cross multiplied by a over v cubed. So I took this old equation, multiplied by a, and divided by b cubed, units thereof. All right, and so at this point, I guess if we're doing unit math, we could come in here and say, look, one of these will cancel one of those and make that a squared. That's cool. I could get rid of this one and make it a squared, but whatever, it's pretty ugly. I'm just gonna get to work now. Oh, we've got a square root here. I could square root both sides. Or maybe that would be good. I don't know. I'm gonna do this, and this square root will cancel that. Means that beta are equal to, oh man, I do not want to forget that square root. Sometimes you'll see me use that little end point. Just it helps me when I'm writing really long equations to tell where the square root ends. That's just what I do. I'm going to say we got a kilograms. We got meters per second squared. I've got another meters per second squared. I've got a seconds. And then I've got a meters squared per second squared, because I've got two of those there. All right, so now I can write this here. Oof. You know what? Let's not screw this up. Let's keep that square root really long. So I can do this. I'm going to multiply by, well, let's clean this up. One of these gets rid of those, but then I need to multiply by seconds over meters squared on the top and bottom. All right, what does that do for me? And then here, let's see what I can clean up. Ugh. Oh, whoa, that's cool. Look at this. But one of these drops out one of those. So this is an ugly unit. Again, you might be saying, he wouldn't do that. I would do this to you on test day. Pretty much do it every year just to see if people practice. So out of all this, what's left? Kilograms over seconds cubed. That's fine. That's acceptable. Someone else might write this as kilograms to the 1/2 all over seconds to the 3/2. And you might be saying, dude, didn't you tell me not to use diagonal fraction bars? Yeah, but sometimes I do that for exponents in this form for this style, just for some weird reason. I don't know why. I'm a complicated guy. All right. There's a couple of examples. What is the goal out of here? The main thing I'm trying to get you to focus on is these problems are hard enough as it is. If you miss the critical step of comparing two terms, it's going to take you all day and you're going to waste time on the test or get lost. It's important, not just for a test, but for understanding, is to remember the key fact. The units of any two terms must match. So when you need to check the units or determine the units, remember, grab one term that you know and compare that to the term that you don't, and do that term first, then do the other one. All right. Now, since we're doing tricks, I'm going to show you one that always screws up the class, and I think I've got it over here as well. This will be a challenge for you. Whoops. Let me see if I can get that. That's pretty close. We'll zoom in just a little bit. Okay, go over. Sorry about that. Okay. Let's say we have this equation over here. If you think you're badass, why don't you see if you can figure it out? I'm looking for, well, I know about B, X, and T. So try to figure out the units of C and K. These are just some constants. So what am I looking for? The units of C and the units of K. Pause the video if you want to try it. I recommend pausing the video and seeing what you know or don't know. Okay, I'm going to assume that you paused the video and gave it a shot. When you see this type of problem, it can be difficult to tell where to start. because most teachers maybe have shown you the other one, but maybe not this one. So in this case, what do you do? Well, I'm going to start with the denominator here. And many equations take this form. I know from experience that we can only add apples to apples. Meaning, if you're going to add two terms together, I know that these two terms must have the same units because they're added together. If you catch that, you get it. If you don't, the problem's impossible. So what I know is the units of x squared should equal the units of c squared. Well, I can take the square root of both sides, and I see that the units of x equal the units of c, which are meters. So the constant here is in meters. That's cool. Now that I know that, if this is meters squared plus meters squared, that's equal to meters squared. I know the denominator has units of meters squared. And the rest of the problem is easy. So I know the units of V equal the units of K times the units of T all over meters squared. Look carefully here. It's important to pay attention. When I have the brackets around the variable, that means the units of. This is a consistent statement. This is not mass. I have already used the fact that the units of x squared and c squared are meters. So maybe I could write it like this just so you see it. You could write the units of x squared plus c squared. But what does that mean? We know this is meters squared from what we just did. I know that this is seconds. And we know that this one over here is what? Meters per second. So there's lots of different ways to do this stuff. You can do the math in any order. All right, so that's probably enough on that. Well, let's finish that, right? So I've got meters per second should equal the units of K times seconds over meters squared. I'm going to multiply each side by wait. That's not squared. Sorry about that. Looks like a 5. Geez, I'm tired. I don't even know how many videos I've made today. Well, in this case, seconds cancel meters squared. So I get what? The units of K equal meters cubed per second squared. I'm going to make sure that shows up on the video. Looks like it does. All right. So if you got that one, you really know what you're doing. And if not, that's the last trick that I've ever seen on any of my tests. So this will happen. We will use this every day for the next 3 semesters, 4 semesters. Every physics class, almost every day you use this stuff. So it was worth the practice and doing the extra problems.